This idea we did look at earlier in the year, back when we were looking at functions and things. Just a bit of a reminder, ideas when we're sketching polynomials. So if you want to draw a polynomial, the y-intercept, always the constant number by itself. Because if you sub in x equals 0, you're just left with a constant number. So in my example here, now I don't have to expand the whole thing out, of course. I know that to work out the constant, I just got to multiply all these constants. So I've got 1 times -1 cubed times 2 squared, which leaves me with -4. So let's plot that one. Okay, we know that's a point on our curve. The x-intercepts are the roots. So solve the equation. Fortunately, mine's factorized already. So I know the solutions. We have -1, +1, and -2. So they're my 3 x-intercepts. Now, as x approaches infinity, out at plus or minus infinity, a polynomial will act like the leading term. So another way of thinking about that is the leading term is a bit like, a little bit like an asymptote. Okay? It's what happens out at infinity. Leading term, x times x cubed times x squared. What do we got? X to the power of, it's not a trick question. Add the powers, that's it. 6. Now if I was to say draw x to the power of 6, you would start up here somewhere and you would finish over there somewhere. Well, if I just said x to the 6, it's like a U shape. All even powers are like the U's, all odd powers are like the Egyptians. Okay? Now, okay. Now, those x-intercepts will act like the powers in the factorization. So if it factorizes and it's an even power, I know it's going to touch it like a U shape. So on my graph here, x plus 2 squared. Over here at -2, I know it's going to touch it. Well, I know it's coming from up there, so it's going to do something like that at that point. Okay. The odd-powered ones will be doing the Egyptian thing. Horizontal point of inflection, another way of thinking about it. But just like the cubic. Other than the power of 1, of course. So here we have x minus 1 cubed. So over at +1, well, if it's got to finish up there, it must do that sort of thing. Now, -1 comes from x plus 1. It's to the power of 1. So it'll just cut it like a straight line. There's what the graph actually looks like. So there you go. Now, of course, we could, now that we've seen calculus, get more information. We could find out exactly where it turns up there and down the bottom and things like that. But for a rough sketch, that's how we can do it with a polynomial. If you can factorize it completely, then all you're talking about is your basic curve that's been shifted horizontally. Let's have a look at this one. Ooh. There we go. Let's put it together. I would have looked at this and said, well, the y-intercept, -1 to the power of 4, 1 cubed, 2 squared, -2, gives me, anyone work that one out? Obviously it's negative, it's down there. You can look at the graph and cheat for this one. It would be -4, isn't it? No, -8. Yes, -8. That looks more like -8. The x-intercepts are going to be 1 is to the power of 4. So it looks like it's the power of 4. Notice how it's a bit flatter than a parabola. Because we said as the powers get higher, flatter at the base, steeper at the sides. So that's why that one's a little bit flatter. X plus 1 cubed, so there's our cubic coming through at -1. X plus 2 squared, so more like a parabola out there at -2. And -2, well, it's just cutting it like a straight line. The leading term is x to the 4, x cubed, x squared, x gives me x to the power of 4, 5, 6, 7, 8, 9, x to the power of 10. So that also would start up here, finish up here, and that's what that graph does. So that's just a quick recap of how to draw quick sketches of polynomials. If we can factorize them, we can get a lot of information out of that. There we go.